Okay, so we've talked about energy, and we've talked about how certain reactions that release energy are called what? Releasing energy. Catabolic or exergonic, right? And so those reactions are spontaneous. But I told you that spontaneous has nothing to do with how long it takes, because spontaneously, if everything would go towards breaking down, that would mean our bodies naturally would also go towards breaking down. We would naturally go towards breaking into our components, which therefore we wouldn't be alive. We would be a pile of carbon and water vapor and simpler stuff. So the reason we don't spontaneously combust, and every reaction that's spontaneous doesn't occur right this second, is because of something called the activation energy barrier. So we have to break bonds and make bonds in order for a reaction to happen. For example, when we break down glucose, glucose breaks down into carbon dioxide and water. There's energy involved, first of all, in breaking the bonds of glucose, but then there's also energy involved in making the bonds in carbon dioxide and water. And so even a spontaneous reaction needs this little bit of energy to get started. And that's called activation energy, or the energy of activation. It's represented by a capital E sub A. And so this is what prevents spontaneous reactions from occurring. Some reactions will spontaneously occur. Some things are very, very unstable. You know, carrying around dynamite, not a great idea. Very unstable, can explode, on impact, because it has a low activation energy. It's very easy to get that reaction started. But a lot of other reactions, for example, sucrose, table sugar, breaking down into glucose and fructose, it's spontaneous, but it has a high activation energy, so therefore it would take a very, very, very long time for it to break down. Peroxide, I told you, breaks down. Remember, we have an enzyme catalase. It breaks peroxide into oxygen and water. But that spontaneous reaction is very slow. Light speeds it up. That's why peroxide comes in brown bottles. But even in the light, it's very slow, because the activation energy is high. So a lot of times activation energy can be supplied using heat. If enough thermal energy gets to the reaction, absorbed from the surroundings, that'll get the reaction going. Remember, I told you about lighting gasoline. All I need is a little spark, and I can get that gasoline to light. Once it lights, it's a spontaneous reaction, but it needs that spark to get going. Sorry. So the problem is that in living things, we can't get reactions started by adding heat. We can't just heat up our bodies to really high temperatures to get our food to break down. Make a little oven in our stomach. That doesn't work. And so that's where enzymes are going to come in. Enzymes are going to be a way of lowering that activation energy so that the reactions that we need to happen in our bodies can happen at a normal temperature, so that we don't have to raise our body temperatures to some kind of extreme levels to get a reaction to go. Everybody good? Yeah? Okay. So here's a diagram showing activation energy. Here's the idea. We start with the reactants. It makes perfect sense. This is the amount of energy. How do we represent energy? What letter? E is activation energy. What's the normal letter for energy? Delta is the change.
Oh, G.
G, exactly. So this has so G would be on this axis. This is our free energy. So these reactants have a certain amount of energy that we're going to call free energy. The products down here contain less energy than the reactants. Therefore, delta G, which would be this section right here, the change in energy would be a negative number, correct? Because we're ending with less energy than we started with. So in this reaction, energy is given off. But what prevents this reaction from occurring at a normal temperature, perhaps, is this. This is that barrier I was talking about, this transition state. To get those molecules to get to that state to break apart, we have to kind of have a kickstart. In some cases, that is such a low, low, low amount that certain things don't exist at room temperature. They automatically, spontaneously break down at very low temperatures. But the things in our body don't. They would require a higher temperature in order to break down. So this is our activation energy. All right, so that's where enzymes are going to come in. What enzymes do is they lower that barrier so that the reaction can proceed. They do not change delta G, because delta G, remember, is just the net change in energy from where we started to the amount of energy something has at the end. sort of like if you invest in the stock market. If I put in $100 and then at the end my account is worth $1,000, I didn't really profit $1,000. I only profited $900 because I initially invested $100. So my delta G would really be $900. That would be the net amount of money that I made, the profit that I made in the reaction. So if we go back for a second here, this is delta G. If this had 100, oops, sorry about that. If this had 100 joules of energy to start, let's say this is 100 joules, and now it contains 10 joules of energy, what's delta G? 90, right? So 90 joules of energy was released in this reaction. Now, if an additional 10 had to be put in to get this started, it doesn't change anything because you get that 10 back right here. So this totally does not affect the net profit of what you make. Does that make sense? Because this is just your initial investment. First, you have to get your investment back, and then everything else is your profit. So this is how much energy was released. All right. So enzymes are not going to affect that. What they do is they speed up a reaction that was going to occur anyway. All they really do is make it happen faster. So this is sucrose, table sugar, the kind you get to put in coffee and tea in a restaurant, or the kind you would use if you actually made like homemade cookies and it calls for sugar. That would be sucrose. Cece, you have this look on your face like, how do you homemade cookies? Like, I thought they just come in boxes. So this is sucrose, and it breaks down into glucose and fructose. But when you put sucrose in lemonade or in cookies or in coffee and tea, it doesn't break down. It stays sucrose. However, that's because the activation energy is very high. If we add this enzyme, this reaction happens in seconds. So all the enzyme does is it makes the reaction happen faster. The reaction would happen anyway, but it would be very, very slow. The enzyme is going to make the reaction happen faster. Here's a diagram, an energy diagram. Guaranteed this diagram will appear on the AP exam. It will appear on my test as a very, very, very common diagram.
I came to steal some.
Okay, so let me walk you through this graph because, like I said, this is an important graph. So to get an energy kick-started, this is the amount of energy that our reactants have. Like I said, we can make up a number. We can say that these reactants contain 100 joules of energy. To get this reaction started, we might have to invest, let's say, 10 joules to get it going. But if there's no source of that energy, everything will just sit here. There would have to be some way of putting that energy in. Once it got started, you would get that 10 joules back. And then if now our products have 10 joules of energy, we said that our net delta G, in this case, would be negative 90 joules. This 10 has nothing to do with it because it was just an investment that you got back. It has nothing to do with the profits.
It's always going to be negative?
If the graph looks like this, delta G would always be negative. If it was an endergonic reaction that required energy, the graph would actually look like this. You'd have products with more energy than the reactants. And you don't use this ever as an enzyme graph. Even though enzymes may be involved in a reaction like this requires a constant input of energy. This is not a reaction where I flick a domino and it just goes. This would be the setting up of the dominoes. I have to put energy in step by step to get it set up.
You won't get graphs like that with
If I gave you a graph like that, I could give you a graph like that and just say, is this an endergonic or exergonic reaction? And you would say endergonic. But you would not see a graph like that having anything to do with enzymes. Yes?
There is a graph like it starts up high and then it goes down low. What about the opposite one?
That's what I was talking about here, low to high.
So
All you would have to know is that this would be an endergonic reaction and it would have a positive delta G. That's all you would have to know about a graph like that. Okay, so what an enzyme actually does is perhaps to get that 10 joules in a normal reaction, it would be provided by heat. For example, lighting a match might get that reaction started. It would provide the energy to do that or transfer the energy. Now, with an enzyme, let's say that it only takes 5 joules of energy to get that reaction started. Well, now it's not going to necessarily require a high temperature. 5 joules might be enough energy at normal temperatures that's enough energy that can get supplied. You still get your 5 joules back, so it doesn't affect the profit. It's just, the investment is less. So what would you see on an enzyme graph like this? Here's exactly what you would see. There would be a question where it would say, what's delta G? Well, delta G would be this line over here that only goes from our start to our finish without the hump in the middle. So that would be delta G. You could be asked, what's EA, the energy of activation without an enzyme? That's going to be our taller hump right here, our kickstart, how much it would be without the enzyme. And then you could be asked, what's EA with the enzyme? And that's going to be the smaller hump right there. Those are the only 3 questions you will ever be asked about this graph.
What's the smaller one called again?
What is what?
The smaller one?
The smaller one, this is EA. It's right here. EA, the energy of activation with an enzyme added. So that's it. That's the only 3 lines. There may be other lines there to confuse you. There may be a line that goes from here to here. That's never going to be the answer. Ever. Ever, 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 never, ever, ever. It's there to just trick you. It's only these 3 lines that matter. Delta G, with an enzyme, EA, without an enzyme, EA. Okay, and I believe I have a drawing of it in the notes as well. Is it in the outline? I have a drawing of with and without in the notes. So those are the 3 things you should know about this graph. All right, so let's talk a little bit about...
You misspelled R.
What?
You misspelled R.
I misspelled R. Oh my goodness.
Oh my gosh. That's gonna bother me now.
You really think I...
I'm just kidding.
Okay, good. I don't know. It's you. I was concerned. All right, so enzymes are proteins. Remember proteins, how they fold up into these primary, secondary, tertiary structures. What enzymes are folded up proteins, folded up into specific tertiary structures so that they can speed up a reaction. They're catalysts. The word catalyst just means anything that speeds up a reaction. Heat can be a catalyst that speeds up a reaction. Light can be a catalyst that might speed up a reaction. Agitation, shaking something might be the catalyst that speeds up a reaction. But enzymes are specifically organic catalysts, meaning they contain what? Carbon. Good.
So light and those things, they're not enzymes.
No, that's exactly. So the word catalyst, if I said, are all enzymes catalysts? Yes. Are all catalysts enzymes? No. Enzymes are just one example of a catalyst, and it's the type of catalyst that our body uses.
All enzymes are catalysts, but not all catalysts
Are enzymes, exactly. And so how they work, they lower EA, which I just showed you visually in the graph. They lower the energy of activation, they lower the energy to get a reaction started so that the reaction could occur in our bodies without raising the temperature to an extreme. And it's actually a pre-lab question too. It's going to ask you the same thing, so.
I asked the question.
All right. So how does it work? All right, so the reactant, the thing the enzyme reacts with is called a substrate. That's basically the reactant in the reaction that the enzyme is going to work on. And what it does is the enzyme is going to bind with that reactant at what's called the active site. I know there's going to be a diagram of this on the next page, but I told you that sometimes we simplify it and I'll draw it like Pac-Man. So this is going to be our enzyme. And this, in this case, would be our active site. This is the area of the enzyme that's going to attach to the substrate. And when it does this, here's what's going to happen. Our enzyme and our substrate are going to sort of mold to each other. This is our substrate, let's just say. This was our substrate before. And now the enzyme and the substrate kind of mold together. I'm kind of changing the shape of this because here's the thing. There was an old model of enzymes that they taught when I was in school. 1947, I think it was.
Wait, what? Are you joking?
I'm joking, yes. Otherwise, I've had a lot of surgery.
Yeah, like it's good for like 73.
So what happens is the old thing of enzymes, what it said was that enzymes are like a lock and a key. The substrate fits perfectly. The thing is, enzymes are not rigid like that. They're not like a lock and a key. They bend and twist with the substrate, like a glove, more like a glove would fit to your hand. Alright, this is gonna time out, so I'm gonna just